This part of the lecture, I want to discuss what the book refers to as operational transforms. Most textbooks would refer to this as properties of transforms. Kind of the same thing, just some unique terminology that your textbook uses. So if you're using your textbook, even the old editions, this is the terminology that you will see. So basically, these are just some properties. Most of these I have not proved, but I did kind of write them out in a slightly different way because I know sometimes when I show something like a table, it seems to go pretty fast. So this is maybe a slower, more deliberate way to walk through some of the important transforms that we'll use in class. So basically, we're assuming that the Laplace transform of some function f of t is given by f of s. And we haven't specified what f of t actually is. So the materials that we're going over here would work for any f of t. So the first one is that a constant times f of t, if you take the transform of that, that's a constant times the transform. So that is a part of the linearity property. The second part of the linearity property is that if you have some sum, f1 plus f2 plus f3 functions of time, and you take the transform of that, you'll get the sum of the transforms of each individual one, f2 of s, f1 of s, f3 of s, shown here. And once again, I want to point out that the transform of the product of f1 times f2 is not equal to f1 of s times f2 of s. I've taught this course long enough to know mistakes that most students are going to make on the exam that covers these materials. This is a very common one. So you cannot do this. What it actually is it's f1 of 2 convolved with, f1 of s convolved with f2 of s. So there would be some shifting and some integration and all of the lovely things that go along with the convolution integral, except throw in some complex numbers. So a difficult calculation to make and not one that I would ever advise. Okay, differentiation. So here I've actually worked out how you do this, done a little bit of a proof. You may or may not want to follow along. Some people don't understand until they see it demonstrated how something is done. So once again, we're working with the function f, except in this case, it's the derivative, so it's df dt. The most useful application of this property is in transforming entire differential equations, but you sometimes can apply it in other ways as well. So what we do is we take df dt and we plug it in to the Laplace integral. And then in order to evaluate this integral, you integrate by parts. So we're going to let u be e to the minus st, and we're going to let dv be df dt. And then, of course, dt is going to equal df. Df dt times dt, and so that's equal to df. So doing some substitutions for the formula for integration by parts, the integral of u dv is uv minus the integral of v du. So if you plug in appropriately, you get the following. And then what you'll notice here, this integral here is over time. And so this s to the integral looks like a constant. So I can pull that guy out and multiply the two negatives together. And so I just have s multiplying this integral, which is by definition the Laplace transform of f of t. So the s f of s comes out of this integral. The initial condition component comes out of the uv part, and then in evaluating that from the limits 0 to infinity, you end up with the initial condition on the function of time. It ends up negative because of the way the limits run on the integral. Now notice I've used the terminology 0 minus here. Some people and some books will just say f of 0. Some will use f of 0 minus. This, if you think, for example, of a capacitor with an initial condition on its voltage. The initial condition on the voltage for 0 minus and 0 plus is going to be the same because a capacitor voltage can't change instantaneously. So that is why in electrical engineering books you don't always see this 0 minus here. Okay, so a differential in time then basically corresponds to multiplication by s in the Laplace domain. F of s represents the transform of the undifferentiated function f of t, and then f of 0 minus is the initial condition. Now this can be generalized to higher order. And so, for example, for the second derivative, you would have then s squared f of s minus s f 0 minus, and then minus an initial condition on the first derivative. And you can iterate this to the nth derivative, and we showed that formula on the table. I think I do not have that here. Okay, integration. So if we're taking the Laplace transform of the integral of f of t, then we basically plug in the integral here, and we're going to integrate from 0 to t. If I were being a really good mathematician, I would do that to some tau, or I would replace the t's here with a dummy variable. What's not shown here is there is a t right here and a dt that got cut off from the scan. Okay, so you just have a double integral. Once again, you can integrate that by parts. Did not actually show that one, so if you do the entire thing, you end up with, as a result, f of s over s, where f of s is the transform of f of t. But because f of t has been integrated, its transform becomes f of s over s. So integration in the time domain transforms to the quotient in the Laplace domain, or division by s in the Laplace domain. Once again, really useful for solving integral differential equations where you have integrals present and you would like to get rid of those integrals for a solution. Okay, these two are two of the more important ones that we will use quite a lot. The first one is the time shift. So if instead of f of t, we have f of t minus a, and instead of u of t, we have to have u of t minus a. So just reiterating, the step function and the function to apply this property have to have the same time shift. And we'll show some examples where we kind of manipulate how to make things have the same time shift. If that's what you have, then basically the time shift has the consequence in the Laplace domain of multiplication by e to the minus as. So f of s is what you would get if you took the Laplace transform of unshifted f of t. And then you multiply by e to the as, e to the minus as, to take care of the time shift. So that's known as the time shift property. Really easily proven by taking this guy, substituting it into the Laplace integral, doing a variable substitution where you let some tau equal t minus a, and then that pulls out the e to the minus as term. Really easy to prove that. And then finally, the frequency shift. When we have a function in time, and that is multiplied by e to the minus at in the time domain, that translates into f of s plus a. So once again, f of s would be the transform of f of t. If that f of t was multiplied by e to the minus at, then simply everywhere you had an s in your transform, replace it with an s plus a, and that's taken care of the frequency shift property. Scaling property, I actually use less in here than I would perhaps in a linear systems class, and less in Laplace than I would say in Fourier analysis. But there is a scaling property in the Laplace transform. This also can easily be proven with a change of variables in the integral. So it's a very easy property to prove. It turns out that if you do have a scaling change in the time domain, if it's multiplication by AT in the frequency domain, or multiplication by A in the frequency domain, S gets divided by A. And then you have this constant here, 1 over A, so that things come out right in the integration and everything is normalized. So basically, time dilation transforms into frequency contraction, and time contraction transforms into frequency dilation. They have the opposite trend. So if you double the t variable, so if it was f of 2at, then in the frequency domain that's s over 2. So time is growing, frequency is shrinking, and vice versa if you had the other situation. So when we have a problem and we're taking a Laplace transform, the truth is, with the exception of applying the sifting property on the impulse function, we rarely integrate. Usually what happens is we have this table of functional transforms, this Laplace transform table. And alongside that, we have a transform. We have a table of properties of the transform, or operational transforms. If we utilize both of those together, we can actually come up with the solution to most problems in the Laplace domain. So it turns out that that's pretty straightforward, and we don't actually have to use integration. That's even more the case if we're taking the inverse transform going back to the time domain, because the integration there is a contour integral involving complex integration, since s is a complex variable. So that becomes a little mathematically testy. Since once again we're electrical engineers, you know, the functions that we tend to deal with, we deal with exponential decay, we deal with polynomials, although not very often. We deal with, first and second order differential equations. We deal with sinusoids, and we deal with constants. And outside of that, most behavior can be grouped into those general categories. Now, you may have a sum of several sinusoids, or you may have sine of t over t like a sinc, or you may have something like that. But especially in causal type systems where you have initial conditions and a t equals 0, and you're looking at both a transient and a steady state response, then most of the functions are relatively straightforward and simple. They've already been put in the table. All you have to do is handle derivatives, time shifts, multiplication by e to the minus at, and some of the properties that we discussed today. Okay, so here's an example. So let's suppose we have the transform, and I know that this is actually in a table, but we're going to use it as an example because it illustrates a few things. So we have this e to the minus at cosine omega t. So from the table, we know that the transform of the cosine omega t is s over s squared plus omega squared. But we also know that we're multiplying by e to the minus at, and we know that there's a property that says if we have a function of time and we multiply that by e to the minus at, what that corresponds to is a shift in frequency. So everywhere we had an s in our transform of f of t, we're going to substitute an s plus a. So if we come back up here to the transform of the cosine, if that's multiplied by e to the minus at, then all of the s's are going to s plus a. So that's what's done right here, is that property has been applied. Now, as I said, this one is typically one that is given in the tables, but I think it's a nice illustration of this property of frequency shift. Okay, so that concludes sort of the more theoretical overview parts of the lectures for Fourier. For Laplace. I have Fourier on the brain since I said it earlier. For the Laplace transform, we have not yet discussed inverse transforms. The only thing that remains to be done now is for me to show you a little bit about taking a Laplace transform on MATLAB, and then for us to work some example problems. But this gives you basically this combined with what is in your textbook and what is in the tables gives you what you need, even if you've never worked with Laplace transforms before. So we'll conclude this part of the lecture on Laplace transforms, which is part 2. Obviously, if you haven't watched part 1, you probably should go back and do that. This lecture might have made more sense. And then we will pick up with some demonstration on, first of all, how to use MATLAB, and then working a number of example problems.